Okay. Yes, it looks like it says it's live now.
Okay, I can see the if we are okay. We are live now. So welcome back to our Astro Twin 2020, and uh, you will start with the workshop right now with Aurora. So Aurora, if you want to share your
Yep, that sounds good. Okay.
okay, you can share your screen with us and start with the workshop.
Okay.
Remember that if you have some any question, you can do it through the YouTube to the channel chat, and I share the question with Aurora. So go on.
All
Welcome back.
right. Thank you. So as a reminder, we're going to start by finishing the workshop from yesterday. So let me just remind you what we're supposed to be doing, and I will share my screen. Okay. So from yesterday, we have been working on this workshop 3, and I hope that you all still have this Google document. So we had gotten to the part where we were working on the rotational broadening. So hopefully from yesterday, you got the rotational broadening function to install correctly, and then correctly opened the Carmenez WAS33 spectrum, and also the model that I gave you. And so then I showed you here, this is where we started. We installed the Pi Astronomy library and uploaded both the WAS33 model, and we uploaded the Carmenez spectrum. And so far we had plotted both of those, and that's what I'm showing here. So in blue, we have the data. This is order 25 only plotted. And in orange, we have the model shown here. Okay, and then we were going to use the rotation broadening function called rotebroad to artificially broaden our model. So we want to put the model wavelengths and the model flux, and then we have this limb darkening parameter, which we're going to just keep at 0.5, and then try different values for the rotational velocity, so the v sine I. So that's kind of where we left off. And so now, if you can go back and try to answer some of the questions here. So I'm going to give you about 15 minutes to finish up with this. So in 15 more minutes, so I think that's 10:20 your time, 4:20 my time. I think that's right. I'll come back and go over the answers. But in the meantime, I'm going to turn off my camera and turn off my microphone, but I still will be here. So if you do have questions, just ask them in the chat and I can come back and answer them. Okay. Hopefully you had at least enough time to play around with it, if not enough time to finish. But in order to keep moving, I'll just come back and show you some of what I've done. Okay, let me share my screen. Great. Wrong one. Okay. So here's what we had done last time already. I just reloaded everything. And we were kind of here where we had plotted up the spectrum of the data and the spectrum of the model. And so I showed you 20 kilometers per second. And now I'm just going to try a few different measurements, or sorry, a few different velocities and see what they all look like. So I'll do 20 kilometers per second, 40, 60, 80, and 100. Let's see, hopefully that doesn't take too long. Great. Okay, and now I'm going to plot this. So I'm going to take the same plot as I have before. So the original model is with 0 kilometers per second. And then let's plot all of the other models. So we have broad model flux 20 is what I've now called this. And then 40, and then 60. So 20, 40, 60. We'll just do them all. Hopefully this won't look too crowded, but if it does, we'll just comment things. 80 and 100. All right, let's see what that looks like. Okay, and then I'm going to zoom in on the line. So from 6550 to 6660. Okay, cool. So we can start to see what's happening here. And I think I will zoom in a little bit more. And just also on the Y. Okay, let's see what that looks like. Okay, great. So we can kind of start to see it. I'm going to comment out a bit, but you can now see what happens. So for the model at 0 kilometers per second, we have this narrow and deep dip. And as we go to 20 kilometers per second, we start to get a little bit wider and a little bit shallower. 40 kilometers per second, we get even wider and even shallower. 60 kilometers per second, same thing, all the way up to 100 kilometers per second. And there's a little bit of a radial velocity offset here, which makes it a little bit more difficult to see. I guess I could add a few to make it easier, but I probably won't spend the time to do that right now. Okay, let me just see if we can make this a bit easier to see. Since it looks like our line is pretty broad, I'm just going to leave the broadest view. Okay, great. So now we can see our 80 kilometer per second model and our 100 kilometer per second model. And basically, the way that we can figure out the the rotational broadening is just by looking to see which model fits the best. So these two clearly show kind of the best shape and the best depth. And so even just with this really simple method, we can see that the data probably has a radial velocity a bit larger than the 80 kilometers per second, and maybe it's fit best by the 100 kilometers per second. We can even plot, let's do 120 and see if that looks like it's too broad. Okay. Great. Okay, so now we can see that we have this red model here that's 120. And this is starting to look a bit too broad to me. And so it looks like to me the best fit model, just kind of by eye, is 100 kilometers per second. And if we look up what the rotational broadening value is for WASP 33 or the V sin I value, what you would see is that it's about 90, I think it's 93 kilometers per second. So even just this basic, looking at a single line and looking just by eye, we can tell within 10 kilometers per second how fast the star is spinning. So now if you wanted to do this for real and to try to get the best estimate out for this star, you would combine the effects from lots of different lines. And usually what people do is they use the cross correlation technique in order to combine lots of lines and see how wide these profiles are. And then they do a bit more of a intense chi-square fitting to see which profile fits the best. But even just simply doing this by eye with our models the way that they are, we get a pretty good estimate. So that's cool that we can, with our high resolution spectra, we can get good estimates of rotational broadening in stars. Okay, so I'm going to stop streaming, stop sharing my screen here. If you have any questions about the third one, or if you want me to go into anything in more detail, just let me know. But I will start talking about the workshop that we're going to be doing today now. Oh, I guess, did I answer all the questions? Let me check. Okay, yeah. We tried to estimate the V sin I value by comparing different rotation velocities to the data, and we saw maybe something around 100 was the best. And in real life, WASP 33 has a V sin I value of 90 something, so it's pretty good. Great. Okay, so let's move on to workshop 4. Let me share the screen so you can see what the worksheet is that I've prepared. Okay. So here is the worksheet for the 4th workshop. And today we're going to be using the cross-correlation technique to try to measure the radial velocity of a star. And we're going to be using the same star that we used for part of the workshop yesterday. This is Barnard's star that we'll be using. And this is the file that hopefully you downloaded yesterday. That's ADP.2014. And if you didn't download it yesterday, it's on my GitHub page, which you can access here. So then this is the GitHub page, and it's this ADP 2014 is the one that we need. And we're also going to use another function from the Pi Astronomy library, and this time we're going to be using the cross-core RV function. So if you want to look at the documentation, I've listed that here. So to install this library, again, we're going to have to do the same thing that we did yesterday. So you can follow along on the co-laboratory worksheet yesterday to install the library. But basically, you just type /pip install Pi Astronomy. And you can import it by just saying from piastronomy.py/asl import cross-core RV. And the last thing that you're going to need is when you do cross-correlation, you always need 2 spectra. So in order to determine the radial velocity of the data, we need to have a spectrum that's at rest. And usually we use a model. Sometimes you can use a radial velocity standard star. So this is a star that doesn't have very broad lines. It has a radial velocity that's known to a really high precision. But for today, we're going to use a model. So I've made a model of Barnard's star, and this is also in the GitHub page. So if you go to my GitHub page, it's called barnard_model.fits. So you need to download that for today. Okay, great. So you can follow along with the steps from yesterday's co-laboratory and just plot Barnard's star and the HARPS spectrum. And from here, you can just follow along with the worksheet, and it'll give you instructions. So if you have any questions, let me know in the chat. And again, I think I'm going to turn off my camera and turn off my microphone. Then I'm going to give you about 15 minutes and go over the first part, just to make sure that everybody knows how to import the functions that they need and plot the files that they need. So I'm going to give you 15 minutes. I'll come back and make sure everybody can do the first part, and then I'll give you more time. Great. So if you have questions, let me know in the chat. And if not, I will turn off my camera and microphone.
Hi, Aurora. There is a question on the screen. So if you want to ask uh, right now, you were to answer right now or later?
Yes. Okay. Okay, yes. So the person asked, Armando asked if we need two spectra or if one of the spectra should be the model. Yeah, sorry, that wording might have been a bit confusing. So I mean that you need two spectra, one of them as the data and one as the model. So we're trying to cross-correlate the data with the model to see what the radial velocity is of the data with respect to the model. Does that answer your question? Hopefully. So those are the two that you're going to use, the model wavelength and flux and the data wavelength and flux. And I guess maybe now is a good time just to, since I'm already here, to make sure that everybody knows how to open the files and plot the files for the first step. So I'm going to share my screen and I'm going to be using a new collaboratory notebook, and I will put the link for that in the chat. And Pablo, do you think you could share that into the comments so everybody can see that? I just put it in our private chat. And let me share my screen now. Okay, so here I'm in this collaboratory notebook that was just shared, so you can all follow along. And in the same way as last class, we have to install the Pi Astronomy library. So we do that with !pip install. And then I've imported all of the functions that I'm going to need. And I've uploaded in the same way how we've been doing for the last few classes, the files that I had downloaded on my computer. So the first one is this ADP 2014 file, which is the HARPS spectrum of Barnard's star. And then I've also uploaded the model of Barnard's star. Okay, and then I can open both the model and the data with the AstroPi fits package. So then I can say fits.open and open both of those. And I didn't exactly tell you where I stored the data in the fits file. So I was hoping that now that you're a bit more comfortable, everybody's a bit more comfortable with fits files, you could look around and see how the data was stored. So I did store it in a similar way as the HARPS data. So it's in the first FITS extension, and it's under the keyword wave for the wavelength and flux for the flux. So to just plot the model, I did model of extension 1.data wave versus model extension 1.data flux. And I've labeled this model. And I did the exact same thing with the Barnard star, except for, as we've seen many times with the HARPS data, you have to put this 0 here because they store as an array within an array. And so this is what the data and the model both look like. So hopefully everybody was able to open those files. And then I'm going to leave you again and let you continue on. And maybe right before the break, I'll come back and make sure that everybody knows how to do the cross correlation part. So we have, I guess, like 20 more minutes before the next break. So I'll give you 15 more minutes And then I'll come back and make sure that everybody can do the cross correlation part. Then we'll take our another break, and then we'll finish up the lab after the break, or sorry, the workshop. Okay, so I will stop sharing my screen now. And I will turn off my camera and microphone again, but feel free to ask me questions in the chat if you have any. Okay, I see a question in the chat about using the cross correlation. There are two peaks. I think, well, let me just show you what I did. You should hopefully only get one peak, but let me I'll check on mine, and then I'll come back in about a minute and answer that question while I show you what I did. Okay, great. So since we have about 5 minutes left before the break, I will go through the next little part to make sure that everybody's kind of on the same page before we take our break. So let me share my screen. Okay, so now looking at the worksheet, first I asked you to try to calculate a estimate of what the radial velocity is. And I'm always a fan of trying to do a very quick estimate just by looking at things as a sanity check to make sure that when you do code this in the computer and you're using somebody else's code, you want to make sure that it does what you expect it to do. So even if I know, even if I am doing this on my own, I will always do something like this, this kind of first step. So, okay, let's just look at, oops, that's the wrong one. Here we go. Here is what I showed you before. And we were here. So I'm going to zoom into the region that I asked you to zoom into. So that is 5850 to 5950 angstroms. And let's see what happens. Okay, great. So we can now see the two different model and data sodium doublets. And I'm just going to make the Y limit a bit better so we can see. Okay, great. So I just kind of, actually, I zoomed in even more. And then I just kind of looked at them and estimated the wavelength myself. So I estimated for this line here that the orange one, the data, had a wavelength of 5887, 5887.5. So like halfway in between these two. And then I estimated that the blue one was right at 5890. So then I just plugged those numbers in, and I got a value for the radial velocity of minus 127 kilometers per second. So now going forward, I know that hopefully I will get a peak around minus 120 kilometers per second. So now to show you how to use this Pi Astronomy cross-core RV function, what I did is when I look at the documentation, it tells me that I want to put in my wavelength array and my flux array. So this should be the data. And then our template. So the wavelength template, that should be the model. And the flux template, that should be the model's flux. Then you have to put in a minimum radial velocity, a maximum radial velocity, and your step size. So for the minimum radial velocity, we want to make sure that we have a radial velocity lower than 127. So I used 150. And then for the maximum, I just wanted to see what the whole space looked like. So I used positive 150. And then I went every 1 kilometer per second as just an initial test. So when I run that and plot it, I get something that looks like this. So basically everywhere besides my peak, I have kind of noise, and then I have a clear peak around minus 120 kilometers per second, which is very similar to what I just estimated. So it's always good to do this kind of sanity check to make sure that what the code is giving you and what you're measuring are the same things. So now that it is our break time, I think that I will stop here for now. Let me stop sharing my screen. And everybody has a 15-minute break. If you have any questions in those break, you can ask them in the next part. And we'll be back in 15 minutes.
Okay, thanks. So we will go to the break and we'll come back in 15 minutes. Okay?
Yep.
See you later. Bye.